Just 1 minute, and then we start. Get some water.
Yeah,
Need
yeah.
some more water?
No, I have. No problem.
Okay. We are ready to start. Omar, can I ask you the favor to... Omar, can I ask you the favor to close the doors so people know that we are about to start? Thank you. So, very good. Okay, so I think we are ready to start. Welcome, everybody. Hope that you had a good lunch. I had a meeting till 10 minutes ago, so I will have some lunch later. My name is Henry Muccini from University of L'Aquila. I work in software engineering and specifically in software architecture. And we are bringing sustainability topics into software engineering and software architecture. And it's the first time I'm physically here with you, and I can tell that I'm really appreciating a lot the conference, the format, and especially that there is time for discussion. So I've been at the software engineering conference in Melbourne a couple of weeks ago with 8 papers in 90 minutes. So I really have, yes, exactly. And I've been chairing a session over there. It was just checking time and no more than that. So I hear that this is the right formula where we can have conversation before, during, some questions and so on. So I really like this formula, and I'm really glad to be here. So we have 4 papers. 3 papers are research papers. The last one is a journal first. The third presentation will be online, so everything is ready. Unfortunately, the author at the last minute problem with the visa, but it will be with us online and will present anyway, his result. So I'm asking all the authors to follow each other presentation. I had to read the papers, so I know what they are about. They are quite diverse, so that means also interesting, but that means also interesting and a challenge in the discussion part. So let's see. Okay, but let me stop here. Let me introduce Chantal. She will present this paper that is very close to software architecture community. So I'm very glad I'm chairing this session, and with this title, with middleware, and trying to create this middleware to make our architecture more sustainable. So all of you will get 10 minutes as in before, with a couple of questions at the end. When you see me standing there, it means that there are 2 minutes left, okay? And it's time to go to conclusions. Thank you.
The microphone are okay? Can you hear me? Yes? Okay, thank you. So I have a presentation today. I will not read the title because I will explain afterwards. So it's a presentation of the work of Pedro Borges, who was one of my PhD students, and who is in Brazil today, and he is not here. So I am presenting his work that I supervised. Before I begin, I have some personal stuff to say. So I just arrived because I switched my bag. In the hurry, I took the bag of someone else. So if someone else is looking for his bag, I just go back to bring it back. Second personal message. So I attended Anna Peters' talk this morning. And I have to say that now I know why I choose computer science, because I have to solve simple problems, even if sometimes it's a bit tricky. So I am really sorry. So today I will not, for Denis, I will not stop computing. I just try to reduce. That's just for the introduction. And also for Denis and maybe for the community, I really think that with the ICT for S, we can have, even if we have some bad effects at the short term, maybe we can have some really good effects in the long term. So just it was, sorry, I have the microphone, so I can say some personal message. So okay, just I start, sorry. Okay, so I begin to present a use case, which is, I don't know if you can see really good. So it's a typical IoT use case. And we have, it's in a city, and at the level of a city, they have deployed some sensors. And so there is an application that needs to collect the value of the sensor periodically, and to show the value of the sensors when necessary. So it's an IoT, an example of IoT application. So, and now the context, so IoT is identified as one of the main factors of energy consumption growth, as Hugues Verbeuf showed yesterday, and it generates lots of data. So it's the context. So now for our research work, we reduce the focus. So here I just wanted to introduce the fact that an IoT system is really a distributed system. So here, I wanted to show here the distribution of the system. So we have at your right, the many sensors that are very heterogeneous and that it's really difficult to communicate with. In the middle, we have an IoT platform that is masking the heterogeneity of all the sensors. And on your left, there is the IoT consumer application that is asking for collecting the observation of the sensors. So when I say IoT consumer application, yes, of course, it consumes energy, but it's really the mean of consuming collected data. And so there are interactions between the IoT consuming application and the IoT platform. And in the software engineering world, the interactions are mainly managed by the middleware. So here we are, you see in the stack of software, so there is a system, there is a middleware, and there is the application. So our work is focused, so really I focus on the IoT consumer application and on the IoT middleware. So, and the middleware, it's really the one that manages the interaction. So now on, we have, so Pedro has done a middleware, and the question next was how to be more energy efficient in this middleware. Can we do that? And I have to say that, you know, in terms of energy efficiency, there are lots of work that are looking at the CPU consumption, because we have tools for that, and not so many that are looking at the cost of the interactions. So it's, yes, it was our objective. So how to be energy efficient for the interactions, and also how to bring some energy awareness that we could give back to the developers and also to the users, to the end users. So it's the two questions we had. So we had a middleware proposal that's called IoT-var. And in the IoT-var, you can imagine that the developer declare variables, and we call that IoT variables. But if you remember the use case example, we will have one variable by IoT sensor. So we declare variables, and each variable has a different refresh time. And so our middleware, through the proxy design pattern, manage the interactions with the IoT platform. Okay, so we have seen that the first outcome of reducing this IoT-var middleware is that you can write application more with less number of line of codes. And then the second question for today is how can also be used the middleware to reduce that. And as Adel Noureddin here as stated before, the middleware is a good place because if you reduce at the system level, it's even better. But if you reduce at the middleware level, it can be used by many applications. So we thought it was a good level to introduce that. So in the middleware, I will not go into the detail, but we add some components, software components for energy efficiency and energy awareness. And we also had, so for the energy efficiency, we were asking what kind of strategy we can introduce. And we have, as I told you, measuring the energy cost of the interaction, it's not so easy. So we have a lot of estimations, but the measurement is not so easy. So we have made some measurement, and one of the results of those measurements is that if you, yes, here in the graph, so you send a message for a certain given period of time, and for 24 bytes till more than 3,000 bytes, and we can see that it does not grow. Does not grow so much. So our idea was, how can we use that in our IoT middleware? So from that, we get a catalog of energy efficient strategies. One of them is request grouping, and this one I will talk a little bit more about. And the other is just adaptation of the refresh time. It's interesting, adaptation of the refresh time, because maybe you will decrease the quality of service, but with that, you can adapt to a limited energy budget. And yes, so in case of request grouping, if you remind the image with a lot of sensors, so every sensor does not have the same refresh time, but if there are similar refresh time, we can group them. And so instead of sending 3 requests, we can send one only request. It's a simple ID, and that's that simple ID that we evaluate. So we evaluate with, yes, experimental setup. So here we had a watt meter, and we just measure the interaction on the application side, consuming application side. And we measure with we write the same applications, but the first time in blue, we don't use any middleware. In the second time, we use the middleware, but without this energy efficient strategy. And the second one with so remember, blue without IoT middleware, orange with, but without energy efficiency, and green with energy efficiency. So what are the results? So you can see what is interesting here. So you have the level of grouping. So we group from 25 sensors till 200 sensors. And we can see that in all the cases, the middleware if you don't use the energy efficient strategy, the middleware has a cost. So orange is above the blue. So adding a software level has always a cost. But if we introduce the energy efficient strategy, we can reduce the cost. So that's the good thing. So I arrived to the conclusion. Yes. So in this work, we have introduced some energy efficiency in an IoT middleware. And we have shown that it was possible while improving the development effort to also reduce the cost of energy consumption. So it was a good result. And as an example, it can augment the lifetime of your battery. For example, from 16 hours to 31 hours, it's not too bad. Okay, but not least, we think the most important would be the energy and awareness, and to be able to, so we have been able to use the measurement to build a model, and with this model we can estimate the energy consumption of the application according to the grouping factor, according to the refresh time, and so to have a value of this consumption. And we think it's important for the future. And so in the future, yes, I think it's important to put the user and the developer in the loop. It's more important than just reduce. So it's one of the points we want to develop. And the second point, of course, you have seen we have looked at the consumer application side, but it would be interesting to see at a service level with all the distributed components. So that's all.
Thank you very much.
Thank you.
Time for 2 questions, as usually, as we do. Okay, and let me ask Gael to be ready for the second presentation meanwhile.
Hi, Adrian Friday, Lancaster University. Thank you for your presentation. I'm kind of interested in, I'm over here. I hope you get your bag back, by the way. I guess one of the sort of bigger picture questions is about the rhetoric of the smart city and the value you get from putting this kind of thing in the city. So although I would kind of, you're sort of optimizing the direct energy here, there's all the embodied energy that went into creating that thing and all the energy of the service vehicles going around changing batteries and, you know. Are you able to comment at all on the value of the data and whether I don't know, they got the sensor density right, whether it was worth it in the first place?
What I didn't get the question. So,
okay, so
you asked me if I use this middleware in an application in a city, or do you ask another thing?
Right. Sorry. So your scenario was,
yes, it was just a use case example.
Oh, okay.
Just to explain the middleware,
right.
We didn't go into that.
Okay. No, that's fair enough. Thank you.
Any other questions?
Sorry.
Daniel Sheen from the University of Bristol. Could you just explain again what the grouping of the requests here? Sorry, over here. Sorry. Could you just explain again what the grouping of the requests, this batching, actually? How does that translate into performance difference for the system operation? If any batching means that the delay between the first and the last message is going to increase, right? So what are the constraints there? Or am I misunderstanding what the actual mechanism of the optimization you carried out was?
Sorry. Why would it be increasing? No, the idea is, so you are looking for 200 of variables, so you can ask 200 of times to the platform. So if you ask 200 of times, you have 200 the message and the answer. so you have 400 messages. But if you ask the 200 at the same time, so the message is a little bit longer, but you only send one and you have only one answer.
So that means that this kind of optimization is only possible for circumstances in which there's no demand for the values in real time. Yeah, you can tolerate the delivery of those the message 200 events back.
Yes, you're right. Okay, sorry, I didn't understand. So in the middleware, we have two interaction patterns. So the first one was request reply, and the second one was publish subscribe. So in the publish subscribe, the platform is in charge to send, but I only shown the values for the request in this case. But you're right, publish subscribe may be a good solution. But if the refresh time on the sensor side is very active, maybe the request reply become a better option. You know, because if there are a lot of things coming here, too many things, and that the platform is not able to filter, you receive too much. So it's I would say a balance.
To what? Sorry, if we do have, if I can come back very quickly. To what degree is this a specific green ICT feature versus just common sense good software engineering?
Yeah, maybe. It's what is middleware for. Yeah. But yes, the idea is, you know, we implement the middleware. So it's our job, I would say. And if we do it at the middleware level, it's easier for the application above. It does not have to do it.
So then
so it can benefit from it.
Do you then consider this as sort of a call to the community to just have another driver to build the system right to how they should be built in the first place, because there's energy saving that comes with this as well?
I would say it's just to say when you build the middleware, when you build distributed interactions, you can think about that. Yes, grouping or is good. Just that.
Okay, thanks a lot.
Just that. Thank you.
Yeah, we'll discuss later because I think it may open different perspectives. Yep. So thank you again. So let me introduce the second speaker, Gael, assessing both pressure and network power consumption. You'll see that the topic looks a bit different, and it is, but there are some common elements between the two topics that we will use in the discussion. Please.
Okay, hello everyone. So thank you for the introduction. So actually, today in this talk, I'm not going to talk much about nasty technical details and network details, but I will rather use it as an excuse to discuss more general methodological concerns. So our more general goal here is to design methods and tools to assess the environmental impact of changes or actions or rules in order to better guide societal choices at the different scales. So here I mean that we are not only targeting individual actions, but also policymakers or industrial stakeholders and so on. And as an exercise, we'll try to address questions such as what would be or would have been the real impact of limiting the quality and resolutions of video. So for that, the classical approach is to follow lifecycle assessment norms by looking at a functional unit such as what is the carbon footprint of 1 hour of video streaming. So for this, we'll have to consider both the productions and use phases of all the involved sub-services, including the servers, the end-user devices, but also the network infrastructures. And through this exercise, it is common to reuse the result of other functional units, such as the carbon footprint of transferring 1 gigabyte of data over internet. So far, so good, but the main point I would like to raise here is that in our context of guiding actions, such intensity or efficiency indicators might actually be considered harmful. So I don't know how you feel about this slightly provocative claim, but I hope that by the end of the talk, you will make it yours, and that's my challenge. So to begin with, it is important to recall that in such studies, we are usually using an attributional methodology. That is, we start by estimating the overall impact, and then we somehow strive to allocate them to the targeted functional unit. So for instance, for data transfer, this is typically done using data volume in gigabyte as the allocation key. That is, the GHG emissions of transferring 1 gigabyte are estimated by dividing the overall emissions by the total volume of data. And for the allocations of your home router, we will end up with the same basic ratio. But as you already know, neither the manufacturing emissions nor the power consumptions of your home router depend on the actual traffic. And this is also partly the case for all the other network equipments. So intuitively speaking, for them, the global emissions are mainly driven by the number of subscribers and the maximal capacity in megabits per second. So one may thought about using other allocation keys, such as the download rate or durations, but in practice, none of them are completely satisfactory. And moreover, if you add to that the numerous other hidden assumptions, at the end of the day, you are getting quite far to the reality, to the physical reality, and we are rather in a kind of accounting world made of accounting rules. So when the results of such studies are used to drive actions, we are implicitly making these proportionality assumptions between the usage intensity and impact. But as we just saw, this assumption is largely invalid, such that increasing or decreasing by a factor of 2 the amount of transfer data is not going to increase or decrease the emissions by the same factor. And actually, this assumption is still invalid, even if we only look at the electricity consumptions during the use phase. So in practice, the power of such equipments can be decomposed into a static part that is independent of the load and a dynamic part. So all those observations suggest for a more consequential approach, where the idea is to look at the difference of the overall impacts under some changes. So to do so, one might start looking ahead over a short period of time, which basically means that we only consider the dynamic part. But this is, of course, still not satisfactory, because on a longer term, an increase of the usage will increase the pressure on the infrastructures. So new equipment will be deployed, meaning additional manufacturing emissions, but also an increase of the overall static power consumptions. And this is precisely this relationship between the level of usage and the dimensioning of the infrastructures that we aim to better understand in this study. So to do so, our proposition is to go beyond intensity factors and related functional unit by adopting a more global approach. So here the idea is to model the given service or use case as a whole, so a parametric model linking usage variables or actionable levers to the dimensioning and load of the infrastructure. And from this, we can then assess the absolute impact for the whole parameters, for the whole perimeter and territory that we consider. And then the idea is to run different scenarios, including a reference baseline, and to compare their respective impacts. So now, let's see how we can apply the general principle to the case of video streaming. Oops, sorry. For the sake of simplicity, for now, we'll focus only on the data transfer part of a fixed network, and so we'll ignore all the other components. And we'll make also other assumptions. So we'll consider a territory like France, and we'll assume a single network operator and a single video provider like Netflix. So here is an overview of a simplified network model. So very briefly, it is organized as a hierarchical tree structure with a star-like shape centered around a single IXP, which is collocated with CDN servers, playing the role of caches to reduce the pressure on the international long-haul links. And to update this cache and to get access to out-of-cache videos, we also consider one main data center in the US with one submarine cable. And finally, we have the local loop that is fully implemented using the very efficient GPON fiber to the home technology. And at the leaves of our tree, we have your houses with one small active device required for GPON. So now we have to properly dimension the equipment for all nodes and links, such that one, every house is connected, and two, that the respective capacity is large enough to manage peak demand access rates that are estimated from the scenario parameters and with the help of some statistical tools. Then from this list of equipments, one could evaluate the whole lifecycle impact, but owing to the lack of data, for today, we'll only consider static power and yearly electricity consumptions. So now it only remains to define some scenarios. So we start with a baseline that is supposed to correspond to a very basic usage of internet without any intensive traffic, no video, and sober website, and so on. Then we have four scenarios making an additional intensive use of video streaming with about 20% of watchers at peak hours and different levels of video quality. And we also added one download scenario of huge files, such as video games or operating system updates that reflects a very different usage pattern. Then in this column, you can read the corresponding average peak rates per house. And here are the results of our model for the absolute electricity consumptions over 1 year. So here, we can first observe the non-proportionality effect, where increasing by 40 the average peak rate yields to a much smaller increase of the overall consumptions. But if we focus on the shared network equipment, shown in light blue, then you can also see that the HD or even the full HD scenarios put rather low pressure on the network. So in contrast to the other three scenarios that requires to double or even triple the infrastructures. And then we can eventually compute the consequential or marginal impacts of those variants by considering the relative difference with the baseline. So let's keep this delta for reference. Now, just for you, I'm going to do what I said not to do. So yes, we're going to compute some intensity factors. And for that, we just have to normalize the overall consumption that we just saw by the total volume of transferred data. And by doing so, we get to these paradoxical situations where increasing the usage does increase the overall consumption, and this is expected, but this increase of the usage also decreases this intensity of indicators. And this is a problem because out of context, such an improvement can easily be used to fool people by letting them think that we are going to the right directions of the growth. But even worse, what if someone used one of these indicators to estimate avoided impacts? For instance, if we start here with the Ultra HD scenario and try to estimate the gains of limiting videos to full HD, then with this classical methodology, the expected gains will be considerably overestimated by a factor larger than 5 compared to the reality of our scenario. So this means that you can easily end up with wrong recommendations, and we actually give one real example in the paper. So I hope I managed to convince you that to be extremely careful with such indicators, and if not, I have a few more arguments for your approach, but I see I'm running out of time. It's okay? Yes, okay. So first, we argue that it is better suited to properly account for shared and multiple purpose equipment or services. Second, one may expect to incorporate indirect effects, whereas this is clearly out of reach for intensity factors. And we also believe that per unit usage indicators tend to put the responsibility on the end user, whereas we believe that our approach are better suited to leverage more global and more collective debates and actions. But of course, everything is not so green. And in particular, the modeling of the reality is complex, and so our approach means we also need more efforts to apply it and to deploy it, but that also means more work for us. And this is the last slide just to tell you that you can try our model online to make your own scenarios and to adjust all the parameters according to your own expertise and own assumptions. So thank you for your attention.
Thank you very much. Please. Can anybody bring the microphone up, please?
Thank you for the presentation. This is the discussion I was having with another colleague just yesterday. The video streaming is one sort of issue, but there are a lot of online advertisement which are video as well. And they're running all the time, even if you don't open a static web page. And there is a bidding process behind it, and that some of them are very, even I cannot stop some of them, they'll go on. What is your opinion? Is it taking more than all of these? Is there any idea you have about that?
I totally agree with you. Video ads is maybe more problematic than Netflix or other video providers, because yeah, there is a direct impact on the CDN, on the network, but there is also an impact on the end user terminals, because it tends to accelerate the obsolescence of a smartphone, because well, with a web page full of videos starting automatically, and with a whole smartphone, you just can't even look at basic data. So yeah, there are many indirect effects actually behind video ads that make them, in my opinion, even more problematic.
There's a, okay, yeah, so I wanted to know.
Thank you. Daniel Sheen, University of Bristol. So it was the peak capacity that you looked at, yeah, right. And the pressure that additional traffic exerts on that. Does that then mean that outside of peak, any data consumption has zero carbon intensity?
Well, we okay. Let's see. So sorry. Okay, so here. We have we also take into account the dynamic consumption parts over during the oil. We have the peak intensity is used to drive the dimensioning of the infrastructures, and then we estimate the power consumptions from the static power consumption. So this is what is in blue. And we add, on top of that, the dynamic power consumptions during, due to the additional traffic, even outside of peak periods. But as you can see here, according to the numbers we got, it's very small.
No, that's true, indeed. But additionally, you said that you want to look at the short term, and not just the short term, but the medium or long term marginal impact. So the effect of the change of capacity on the left-hand side, yeah, the baseline on the required network infrastructure on the capacity, which I think is exactly the right approach. But the capacity is determined by the demand at peak time, yeah, so at 7 o'clock in the evening. So that means in the morning, Jens is shaking their head, or whatever the time is, but the capacity is determined by the peak demand. So we can take that offline. But in any case, the question then stands: how should we deal with consumption of inelastic infrastructure? And then you could say the same about the road network or any other system where we're interested in modeling the marginal effect. How do we deal with the use of that network, of that infrastructure outside of peak? Yeah, and so one response could be, if you're not doing it at peak time, it's for free, because you're not actually you're not actually affecting any pressure on the upgrade of the infrastructure.
So actually, this raises the questions of, so far for simplicity, we look at a single usage, so video download or video streaming. But this raises the questions of how you will deal with multiple usage that produce peaks at different periods of time.
There's only one peak in the middle, in the day, there's only one peak.
Why is...
So let's bring this discussion
yes, absolutely, yes, yeah, fantastic.
To the session at the end, okay? So thank you very much. So now let me ask to the technical people if we had the third presentation online. So the third presentation is given by Zisen, and it's about environmental impact of 5G networks. Okay.
Hi everyone, could you hear me?
For the speaker, can you hear us?
I can hear you. Could you hear us?
Okay, yes, quite well.
Okay,
so
awesome.
Nice to see, nice to have you, even if online. You'll have 10 minutes. When 2 minutes are left, I'll give you a sign, a voice, okay? So if you listen to me at the end, it means that you have 2 minutes left. So.
Sounds good. I don't know whether people can see my slides yet.
We can see you now. Bye, ciao. But before we could see the slide before.
Okay. Let me share again. I don't know whether it's because I stopped sharing. Does that
yes.
work?
Yeah, we see it. Yeah.
Okay, great.
It works.
Awesome.
Please.
Thank you so much. And yeah, thanks for everyone to have me in this weird situation. I was having visa issue at the last minute and I cannot go. But in some other perspective that I saved some GHG emissions, so that's good for this conference as well. But I really hope that I can see people next time, that I can show up in person. Okay, so hi everyone. My name is Zeseng Zhang. I'm a PhD student from UC San Diego. And today I would like to represent our team to show our best effort of investigating the sustainability of the 5G base station overhaul in the United States. So 5G as a new technique brings basically two major improvements in latency and bandwidth. The average latency that people would have for 4G is usually around 60 to 100 milliseconds, while for 5G, it can achieve less than 1 millisecond average latency. And 5G can make 10 gigabits per second download speed, while 4G usually has less than 1 gigabit per second. So to achieve these high bandwidth and lower latency, 5G basically introduces three new technologies. First of all, 5G uses mmWave whose frequency is higher than 6 gigahertz, while 4G's frequency is usually lower than 6 gigahertz. So mmWave basically enables wider range of channel to have higher bandwidth. And secondly, 5G uses massive MIMO, which is massive multiple input, multiple output, which has more antennas compared to 4G. This enables higher channel capacity, which achieves higher bandwidth. And last but not least, 5G has shorter wavelengths, which requires deploying a large amount of small cells. These small cells can handle data traffic more efficiently, reducing congestion and latency. So 5G brings us such a big benefit in the network perspective with these three new technologies. And everyone, I think, is excited about the emergence of 5G. However, what is the environmental cost of deploying 5G, especially deploying 5G base stations, is a question that haven't been answered quite greatly yet. Therefore, in our work, we are trying to investigate this problem from the mineral perspective. Basically, we are going to answer these two questions. First of all, what new materials are these technologies depending on? And secondly, how much of these materials do we need to deploy 5G base stations across an entire country? So before we jump into the detail of the answer to these questions, here's a high-level overview of the environmental cost of 5G. We found the massive MIMO requires gallium and germanium, while mmWave needs yttrium and barium. Small cells technology in 5G means we need much more base stations than 4G, so that it requires much more aluminum, copper, and gold to build the 5G. And we find the requirement of these materials are huge, and they are not sustainable. They are hard to be recycled, and they are also difficult to mine and refine. So next, I would like to show more details about where these materials are used and how much they are used in 5G base stations. So here's how a typical 5G base station looks like. It's usually on a street light, and it has one major component called AAU. So in AAU, it contains lots of components. For example, there's antenna in it. Antenna is a major component who helps achieve mmWave technology in 5G, and it contains new advanced ceramic materials, which includes barium and yttrium. And AAU also contains power amplifier, which is a major component to achieve massive MIMO. So 5G adds gallium and germanium to make higher power density and to improve efficiency at higher frequencies. So besides these new materials, because we need a huge number of small cells in 5G, the major minerals that are required by 4G is also needed by 5G as well. So for example, every cell needs antenna radome, and the major minerals in antenna radome is aluminum. And PCB is another major component in base station to deal with signal processing, and the major mineral components of PCB is copper and gold. So after figuring out the major minerals required in 5G base station, next we would like to show how much of these materials are used in one base station. However, when we are digging into this question, we find that these data are actually not quite available on public document, because companies are safeguarding their priority information so that we cannot find them quite easily. So we need to estimate ourselves for the number. We estimate some material usage from supply chain documents from relevant companies. For example, we have yttrium and barium that we can grab from one company's supply chain data, and we are quite confident about these results. But for other minerals, we need to estimate by gathering all the information we can find. This includes gallium, germanium, copper, gold, and aluminum. We would like to claim that this is our best effort estimation we can do with the public materials, and we assume they have the right order of magnitude compared to the ground truth. So let me give you an example about what I mean by best effort estimation. So for gold, we find a 5G PCB production company, go to their financial report, get the material cost of their PCB and the total areas of PCB they produced. We also find a document that showed gold takes 8% of total PCB cost, and the price of gold in that time is about $1,600 per ounces. And we found that one base station needs PCB of 2.57 square meters. And by combining all these data, we estimated that we need approximately about 0.025 ounces in each base station. And here's a breakdown estimation of each material in 5G base station. So after figuring out the number of minerals we need in one base station, we want to know how many total materials we need to deploy 5G base stations across the country. So we take US as an example. We assume that 5G is going to cover the same range of area as 4G does, and we assume people will reuse 4G base station location to set up for 5G as well. So we first get 4G base station location data from OpenCell data set, and then we use K-center algorithm to estimate the total number of base stations for 5G. And we find that we need about 600 million of 5G base stations to cover across the US customers. And here's the total weight of 5G minerals for US deployment. We can see that we need about 6 million tons of copper to deploy the US-wide base stations. And this number is about 1% of coppers we are currently in use all over the world. And also we find that we need about 43,000 tons of germanium, and this is about 1.5 times of germanium that US has imported in 2022. And furthermore, there's
Yeah, just
additional...
let you know, 2 minutes are left.
Okay, thanks. And furthermore, there's additional sustainability problem with producing these minerals. So for acquisition, each of metals must be mined and produced to pure. Mining materials contribute to ecotoxicity. And these metal materials are not infinite. We have already used about 50% of available coppers on Earth. And in the former slides, we show that estimation usage of copper in the US is taking 1% of them. And you can imagine how much we will need for deploying 5G all over the world. And for production, we find that to fabricate the semiconductor wafers, many toxic chemicals are used. And to make things worse, most materials for 5G actually are used once and thrown away, since recycling these minerals from base station costs much more than fetching them from nature. Still, we want to announce that 5G can benefit the environment from other ways, like it can do remote assistance, improve products, reduce GHG emissions, and build smart city to save powers. And 5G is definitely the next incoming technologies. And 5G's trend is unstoppable. So that our purpose of doing this research is trying to raise people's concern from environmental perspective of deploying this new and global scale technology. As we can see, 5G is already using the same order of magnitude of metal materials available on Earth. What if the next generation 6G or future G requires even more base stations than 5G did? Do we have enough minerals for us to deploy them? We need to really take a step back to think about the environmental cost of new technologies, thinking about the trade-off of the cost and benefits that 5G or future G will bring to us. And we also need to improve the ways of recycling materials from this previous cellular generation to help build the next technology. And that will be it. Thanks.
So thank you very much. You would have loved some discussion we had yesterday night at the reception about topics very much related how to separate materials, how to recover materials. So let's see if there is a couple of questions here in the room, please. And you can get ready. Yeah.
Thank you. Zesen, thanks a lot to you and co-authors. I'm Vlad, Technical University of Berlin. From the materials that you analyzed, which do you assess as most critical? Because it seemed like 400 kilos of gold, if I saw that correctly, doesn't seem so bad, right? But then you pointed out copper and germanium, I think, as very bad. Like which are, in your assessment, the worst and why?
So actually, that's a good question. So we want to claim one thing first is all of these things we did are by our estimation from the public materials. So we don't know the ground truth actually. We need to cooperate with companies about the real numbers. And this is the challenge that we face and we cannot be solved. So, but for your question, so we found actually for all these materials, especially like gallium, germanium, these rare earth materials are really under the big issues. Like I point out that germanium is costing about 43 43 tons. And actually, every year the germanium that are produced is the number is around like 200 tons. So I would like to see all these materials that I listed over there. They are already using the same order of magnitude that existed on Earth. So, and this number is only for the US. And if we want to deploy in other big countries, then the number will add up to maybe 5% or 10% of these materials that existed on Earth to just deploy 5G base stations. And that's the basic takeaway for these for our research.
Lovely, thank you.
So second and final here.
Okay, so Jens Malmodin from Ericsson. I guess we are the #1 supplier of 5G base stations currently in the US. And if we would supply that many stations, I would tell you, we will be richer than any nation and company in the world by far. But they are not buying that many base stations from us. And they don't contain that much metals, I would say. So today there is about 400,000 base stations. Maybe we're looking to 500, 600,000 in a few years into the future. Who knows? But it's not certainly 600 million. Because it's like 0.1% of the space is there people live and actually need 5G because they live together, need capacity and so on. All around you is then you don't apply these types of base stations. So I think that will not happen. So this is some kind of more hypothetical thing of like if you build highways all over US so everybody can. So I'm not following exactly here.
Thank you so much for bringing out that question. So one thing first is the 5G base station deployment in the US, as I'm living in US right now, and I think these base stations are basically just in the big cities like Los Angeles, like San Francisco or New York, these kinds of cities. And our estimations are to cover all the areas that 4G has covered. So you're right that like in highways, we might not want to cover 5G, but in our estimation, we take that number in basically to cover wherever the area that 4G covered, we estimate that 5G might cover. That's the one thing that maybe made this number ballpark at the high end, I would say. But I think the number, from my perspective, it will reach to at least 10 million or 100 million in this perspective. But yeah, that's my vibe of this question.
Okay, so thank you again. Please stay with us in 10 minutes or a little bit more. We will have a discussion. So I hope that you can stay with us for the discussion session.
Yes, thanks.
Okay, good. Thank you again. Let's start with the 4 presentation. The journal first will be presented by Hussam. Can you please switch? Sorry, you have your computer?
Yes. So, thank you. Well, I'm going to present myself first. Hussam Kanso. I'm a researcher at the LIUPA, the Computer Science Lab of the Université de Pau et de Pays de la Dour, and this paper entitled Automated Power Modeling for Computing Devices, Implementation and Use Case for Raspberry Pi. It's quite a long title. Was published in the Suscom Journal and co-authored with Adel Noureddin and Ernesto Exposito. So to start with the introduction, I will point to two things that my previous colleagues, the two previous presentations already said. Chantal said that it's quite difficult to measure. And Gael said, we saw that if we don't measure, we don't know what is really happening. So the first step towards reducing the energy consumption, in my opinion, is first to be able to quantify how much energy each device is consuming. So this is quite difficult because we don't always have access to these devices. So sometimes devices are not accessible physically. And another challenge will be that these devices are heterogeneous. Even if two devices can accomplish the same tasks, a lot of times they can consume different power consumption. One additional challenge is that devices may change with time. So for the same device, it can have updates, software updates, its location can change. So maybe it was in a cold location, then it was in a hot location. So the environment changed, therefore maybe the power consumption will change with it. And finally, the solution that already exists are either difficult to implement or specific to one or to one type of devices. Therefore, just to see a little bit of the existing solutions. So some existing solutions are based on hardware power measurements. So we just plug a watt meter and like this, we know how much the device is consuming. Yes, it is accurate. It's the most accurate way to know how much the device is consuming. It is adaptable because if we change the device that is connected to this watt meter, it's going to give us the new power consumption. However, it's time consuming to connect each of the devices to these watt meters. It's cost inefficient because if we want to buy watt meters, it's going to cost us. We need physical access to the devices in order to plug them, and it doesn't scale. Well, the other solution is to use software power estimations. So software power estimations are less accurate than hardware ones. They are not adaptable. So if we create one for a specific device and then we want to apply it to another device, maybe it's not going to be accurate. It's less time consuming. It's not as costly as a hardware solution. We don't need physical access all the time to the devices. However, they lack when it comes also to scalability. So what we are proposing is to try a little bit to take the advantage of each of these solutions. So what we propose is an architecture where we have three types of devices. A power meter. It's a physical power meter, but I'm going to explain about it a little bit later. So the three types of devices that we have are data collection and benchmarking clients. We will have a power modeling server and a power estimation client. So the idea here, the goal of this research is to generate power estimation models for connected devices. So if we want to look at it from a different way, we have data collection and benchmarking clients that are connected to watt meters. They share their metrics with a server that we call the power modeling server. And this power modeling server is going to be based on the metrics collected from the devices, and the data, the power collected from the power meter is going to generate power estimation devices that are going to be used later by the power estimation clients that are clients that don't have watt meters connected to them, but that they may have the same type of data collection and benchmarking clients. So if we take a deeper look at the data collection and benchmarking client, we have a few components in it. First, we have the power collector that collects the power consumption from the watt meter, the physical watt meter. We also have the metrics collector that collects data from the software and the hardware of the device. So it collects information about the device and it collects information about the software. For instance, for example, how much CPU are we using? These two information are then sent to the sharing interface that is going to share both this information with the modeling server. So if we take also a closer look at the power modeling server, we're going to see that it collects these information, it's going to synchronize, clean data, and all this. And then it's going to model, to use this data in order to generate a power estimation model, and then to validate it. And then it's going to do this not only based on the data that is collected right now, but also on the historical data and from different devices that are contributing to this power model. So for our experimental setup, we tested this on some raspberries, the raspberries that we could get. So ranging from the Raspberry Pi 0W 1 until the Raspberry Pi 4. So first we prepared our raspberries with the scripts, and we applied some interference reduction protocol. So mainly in this study, we were based only on the CPU cycles. So what we did is that we stressed the CPU from 0 to 100%, and then we collected the information from the CPU cycles and the power, and then we mapped, we generated the power estimation models. Then we shared them with the server where the models were generated, and we have generated linear and polynomial regression. We're using linear and polynomial regression because there's a high correlation between the CPU utilization and the power consumption. So for our results, we have generated models for all the devices that, or the raspberries that we saw in the previous slides. We have calculated the error rates of these power estimation models. For instance, they are ranging for the linear ones from 0.34 to 7.8, and for the polynomial ones from 0.3 to 3.8%. Then we have calculated the difference in the overhead between the linear and the polynomial to see is it do we prefer using polynomial or linear? And we find that the difference was really small. So the idea is with each iteration, we want to improve our model. So we have also tested this. So we have launched the experiments on different devices from the same type that are sharing the information. And each time we receive new information, we check if we want to generate a new power estimation model or not, in order to gather as much as information as we can in order to generate more accurate models in order to converge at the end. We have also tested the impact of revisions. So the impact of revisions between raspberries was not, they didn't have a lot of impact. However, the number of bits had a lot of impact. So if we use a Raspberry Pi with 64 bits, a model generated for this Raspberry Pi on a Raspberry Pi with 32 bits is going to give erroneous data, erroneous results. We have also tested connecting peripherals. So we have connected some USB wired keyboard, activated the Wi-Fi, the Bluetooth, and we found that that the way we generated the model still was acceptable. However, it gets higher if we use a model that was generated for a Raspberry without these peripherals on a Raspberry with these peripherals. Finally, we compared our approach to two approaches that already exist. So, so the problem with approaches that already exist is that, okay, they make the experiment, they publish a paper, and then for one device, and that's it. So what we propose here is to collaborate all devices together in order to keep generating these models. I think I don't have a lot of time left. So I'm going to jump directly here. We have tested it also on a, not only on a Raspberry, we made a small experiment on a smart lamp. So taking the state, the color, and the brightness, and we found that with different colors, we had different power consumption maybe because the lights that are being turned on in order to make the new colors are so we turn on more lights to make new colors other than red, green, and blue. And finally, for future work, our perspective is to cover additional hardware components, study more machine learning algorithms, because if you want to add more metrics and more metrics, linear and polynomial regression maybe are not going to be the optimal way to generate power estimation models. We want to study external factors and cover more devices. So to sum up, we have it's important to quantify the power consumption of different devices. Here we created, validated, and shared power estimation devices across various devices. And these are my references, and thank you.
Thank you very much. So questions? Meanwhile, can I invite the previous speakers just to come on stage for the discussion session?
Hi, Philippe Krief, Eclipse Foundation. Thanks a lot for your presentation. Simple question, I would like to know if you think we could easily apply or deploy your solution on digital twins architectures, and to be able to have this kind of interesting feedback when you design something new with digital twins.
I do think so. While we haven't tested this, we tested it just on small devices. I do think we can test it on something like this, and I think it will be interesting to test.
Any other?
Okay. Sorry, I was just getting the microphone going. Thank you for your talk. If I understood correctly, you were modeling based on stressing the CPU. One of the interesting things I think is often it's communication overhead, or you're using kind of IoT-like devices for sensor-driven interaction or user-driven interaction. I think there's a lot of system-on-chip integration on the different generations for like video processing, that kind of stuff. So how generalizable is this with more realistic workloads? And do you think you're going to have to cluster based on kind of typical profiles? And do you plan to look at that?
Okay. Thank you for your question. Well, if I understood well your question, you mean if you want to generalize it with, for example, devices that use more than just the CPU. For example, they use graphic cards. I think it can be the case, not with the linear or polynomial regression. I think we will have to dig deeper into more machine learning ways. Not as it is right now, but the idea of each device sharing with the others will be interesting also. I think it can apply, but in this way, but not exactly as it is right now. We need to change, but not the architecture. We need to change what is inside the architecture, the components, mainly what we are collecting, correlating what we collect with the energy, and then choosing which algorithm is the best to generate these models.
Okay, thank you.
Okay, so thank you again.
Okay, thank you.
Okay, so I need one microphone here for them. Thank you. And the other one for question. So the talks were a bit quite different in this session. That's very nice. But what I see personally, it's one thing that comes into my mind. Sometimes as a researcher, we try to find overcomplicated solutions, sometimes to simple problems. But my understanding here, a bit orthogonal to the presentation, but also taking from one of the questions on the first talk, that here in our community, awareness and creating a mindset is more important than technology announcement or finding super complicated solutions. So my point is coming back and to your question before to Chantal, if we can find a solution that it's potentially not so complicated but may save a lot of energy or may improve the sustainability of our system, I think that's the way to go. Being in the software engineering community since 25 years, I see that sometimes we try to find very small, specific, teeny solution that solve a very specific problem. Sometimes the solution is super complicated. What I see here in general, trying to generalize to put together, different presentations, is that what we need in this community is more to be aware and to inform the other people about the importance of sustainability and how to become sustainable, and then to work on that may not require overcomplicated solution, but sometimes easy things may really make the difference. So I would like to open with this input, trying to generalize, otherwise we go deep in 4 different topics which are very specific and that we can do later in the break. And I would like to ask all of you, what do you think is the role in your approach, in your research on awareness, mindset, and simplicity rather than super complicated technical things? So any of you can start, and then we move to the audience for other questions.
Thank you. Yes, and looking at those, I don't know if I answered the question, but maybe I can go ahead. Yes, when I listened to the 4 presentations, I really had the impression that, yes, distributed systems, they are really complex. And we have lots of estimations, and they are not so perfect. As we can see, we have really differences from 1 to 100. So that it's a big, big factor. So I have the impression that we all want to build the estimations, because we do need models and estimation, but we all want to build the estimations on accurate things. And so I think it is necessary. So we do need model, and we do need to improve the models. And that's what I heard. And also, I think that seems important, as we have seen with the remote presentation, is that, and also in yours, is to include in those models the gray energy, the energy of the production. And I think it's really important to go to that, because if we introduce in the awareness also the production, and there are works that are doing that, I think it's really good for the awareness and for improving the models.
Okay. Any other comments?
Yeah, our work is definitely to make people more aware of all the impacts and all the links between the usage actions and impact. So I can't disagree with you. And regarding the balance between the simplicity and the complexity, so as I said, the real world is extremely complex, so it's impossible for us to capture all the fine details. So for us, the challenge is to find the good equilibrium between some things complicated but we still have to capture the important drivers. So it's not always, maybe sometimes you will need some complexity in our model, but then since our goal is to make people aware and to understand the relationship between actions and impacts, we have to somehow hide this complexity of the model. And for that, we can use some data visualization techniques or take inspirations from what is done in the HCA community to communicate to the targets our model. And also there is a strong link with our work and the remote presentations, because well, in my talk, I only talk about power consumptions, but definitely what we want to do is to capture all the impact, and in particular the embodied emissions, and so two works are really complementary.
And this, and whenever you want, just raise physically Ren, since we can see you in the big screen, and I know that you have a question you want to contribute. Yeah.
Okay.
Actually,
okay, please go ahead.
Go ahead. Okay, thanks. So yeah, just to add up, so I think the other way to think about it is things are start from simplicity. So like we announce something, like for my work, the way that I saw this work, I would like to claim that this work is a super high end of the estimation. Some of the numbers that like it's going to be, I think when people get down to the realistic, they will find the number maybe less than what I had in the paper. But I want to say that these kinds of estimation work is to raise people's concern to see about these kinds of work. And when more people are raising the concern about like environmental mineral cost, people will start and stop and think about do we need to like arbitrarily deploying the 5G base station all over the places, or we need to really to do a fine-tuned measurement or plan before deploying all of these things. So the way that I think of the things that you mentioned, the simplicity and the complexity of estimation, is the estimation can give us a sense about how much we are going to do. And if that number is like more than we expected, then people will stop and think and wait to think and to plan before they really get into the work.
Okay, thank you. Usam?
I'm not going to add a lot of things, but I do agree with what was said about simplicity and complexity. I think the more we complexify the things, the more it's not the solution. I mean, if we complexify it so much, it means we are getting far from the solution, and that we are consuming way a lot to reduce a little bit of consumption. And personally, my takeaway message, like from this session, will be, because our presentations were a little bit different, but we have to think like and raise.
They were positively different.
Yes, but
okay. Like you know, I'm doing this because I heard the impression that simplicity was considered to be like a negative factor. My personal feeling, instead, I value simplicity. And if with simplicity we can solve complex problem, improving with respect to the state of the art, we are great. Okay, that's my opinion. That's why, again, I'm pushing on this, because I think that the scientific community sometimes will look at things that must be complex, otherwise they are not good. Instead, I think that they must solve problems. And if they are easy, we are more happy than ever. So that's why.
Yes, I do agree with you. And I think that it's important to raise awareness about all the things that can consume, like from the device to the middleware to what the user is choosing, to if he's choosing to watch the video with high quality or low quality, to the material that is already deployed. So think about all these things.
And I want to leave the discussion to the audience. And another good part of this session, yes, they are different, but because probably we are really doing an holistic view. So we are treating network, we are treating materials, we are treating software, we are treating hardware. That's not common. So again, I see positive things over there. So one comment, please.
Yeah, I tried to frame this in the context of the trade-off between simplicity and complexity. So we want to, starting with the idea that software and digital services are inducing energy consumption and environmental impact, and we see potential for efficiency improvements to reduce power consumption on user devices and in the IoT space. I think the work. I'm very sorry, but I forgot. I missed the name from the gentleman in the middle presenting the work on modeling video on demand.
Gael.
Yeah, I think this is brilliant because it is representing. You opened with this idea that we want to affect change. We want to enable change with these models. There's been a tradition of two simple models that suggested that there's a direct correlation between data volume transported through a network and the energy consumption. And in the keynote on Tuesday morning, attention was paid to the fact that the data volume traveling through a network is increasing exponentially, implicitly, not explicitly, but implicitly saying that this is an environmental concern. Now, what we've seen here is that while there was a 40-time increase or difference in the data volume between the four scenarios, between whatever scenarios that there was, the overall change in the consequential energy consumption was 1.3 times. It was 30%.
Something like that.
Yeah, 30%, give or take, or 34%. So that's important to take into account, because the reverse means that organizations that try to actively support decarbonization and then latch on to reducing data volumes for websites, etc., they have very little effect. Yeah, exactly. So you're shaking, but please, yeah, we can discuss this. But this is a problem, because if maybe I'm missing something, but it seems to be a real challenge to how the communities working on the vertical layers that supply these services from the devices and networks and data centers, and then the organizations building services on top, how they can together work towards reducing energy consumption and addressing the material impact. The discrepancy between the simple model and the reality of how these systems change over time is really tricky. I don't see how we can solve this problem. And this question that I had earlier, whether data transported in the middle of the night, far away from peak, should go for free, so we can distinguish between the cost that we pay for this and the carbon footprint that we assign to it. We assign this carbon footprint as a signal to consumers or any other stakeholder taking part in the system to take action to move us away from a carbon footprint. Yeah? So if there is no connection between me consuming service in the middle of the night and the carbon footprint, then this marginal carbon footprint is zero, it seems to me. That is the interpretation I take away from the model you proposed.
But when you go to a museum, if you go on certain days, you pay more than if you go in other days where there is less people. So those kind of models that may change depending on usage, that in other communities are totally currently used.
Exactly.
Yes.
We don't have that. Exactly.
Yeah, so this remarks that during low period traffic, the data transfer is free is valid if there is no power sleep mode. And I know that industries are working hard to develop sleep mode for network equipments. And once, so with effective sleep modes, then you will again find more correlations between the data transfers and the power consumptions. But this is, yeah, well, maybe this is already happening. I don't know. Maybe some other experts can comment on this. And but this is only for the power consumptions. For all the embodied emissions, well, there is no correlations between the data transfers that you do during low period peaks, low period traffic, and the embodied emissions. Yeah.
Okay, so there was another comment or question. Yeah.
Hi, Srinjoy Mitra from University of Edinburgh. I would also probably chip into the whether any data transmission can be free at any time in the day. but maybe that's a discussion I'll do later. I'm probably going into the 5G thing, and this kind of simplistic models are also useful because it's scary, because you try to measure 5G base stations, where I would argue the more important thing is 5G phones. 5G base stations won't be changed many times. Even if there are 10 times or 100 times less than what you have proposed, they won't be changed many times. Whereas we have already reached 1 billion mobile devices in 10 years ago, 2013. And we have beyond 1.5 billion every year from 2015 onwards. And many of them will be, even if there is 1% of the mineral that you suggested is going into a phone, or this is just phone. I mean, there are 10 billion connected devices. This is just mobile phones. So, and am I right? Are you saying the total number of germanium is the amount we have in Earth's crust, the value that you mentioned? Is that on the order of the amount we have on Earth?
Yes. So
okay.
There's one thing.
Wow.
So there's one thing I want to add to your comments. Yeah. So thanks a lot for that comments. We had to think about during our research as well. So there's one problem that we didn't jump into phones world, instead we stick with base station, is the material in phones are actually easier to be recycled than the base station, because for the phones we usually see people use and throw away, and there's a number that I cannot remember very clearly, but it's about 60% or 70% of the materials on the phone could be recycled and reused in the next generation of the phones. But for base station, this number is super low. The number we found for base station recycling number is about 20% or even lower, like 15%. And those numbers are mostly for the aluminum and copper. Those rare earth materials like germanium and gallium, they will be super hard to be recycled. And the other problem is for the 5G phones, also for the phones that we had coming and expired later on, these devices do not contain too much rare earth materials, and so I don't have a very good number in my mind for the materials that are used on the phone. But I would assume that if there's not too much rare earth materials, then maybe phone won't raise people's too much concern because their materials could be recycled. That's my vibe that while I was doing the research to thinking about phones and base stations question.
No, there are quite a lot of rare earths in phones as well. A chip requires almost 80% of all of periodic table, and it includes rare earths, and there are quite a bit of chips that will go in a phone. But thank you.
We have time for one fast question, and then from some announcement, and then we go to the break. So please, over there. Okay.
Okay, I have a small comment. I miss a bit like the messages you can get from the output number of the modelization you get. But I have also a question regarding that. So I've thought, so in my deep opinion, when we want to answer a scientific question, we build a hypothesis, then so the question, then the hypothesis, then we do a plan experimentation or methodology, and then we get the result, and then they can answer a question. But in this case, you try to build kind of general or generic model to answer the question, but we don't know the question, and I don't know what can be the output, what can be the decision So for example, Citizen Zang, so I don't know if you pronounce.
Is
well.
the question directed to any of them specifically, or is
No,
generic?
it's not. It's very generic. But I just take an example from his presentation. So
Because in the papers I noticed that there are research questions. I mean, maybe not in all of them, but maybe in the presentation, for sake of simplicity, they were not, reported. So just to let you know.
Okay, but yeah. So in general, when we propose, so I have this motto: one question, one model, and hypothesis, we go with it. If you give a general model, you can just limit what are the answers possible with that. And do you think about that? If yes, so for example, for your own model, what are the possible output of your model? What are the possible decisions that can make the user of the model thanks to what you built, actually? So that's all.
So any comment from your side?
Well, I can comment on that because this is also a take-home message that I usually convey. So I totally agree with you. And I agree that yes, we can see several research papers that they try to estimate the environmental impact of some things, but without thinking about which questions or which impacts they want, or which decisions they want to drive. And for me, depending on what is the question or what is the actions you would like to drive, you will, as you said, you need to adjust your methodologies to be able to precisely to answer these precise questions. And so maybe I presented my work in a way that I try to do some things general model, but that's not the case.
Okay, so sorry if we cannot accommodate other questions, but after we have the demo session, so there will be a chance to get together and to speak. But before closing the sessions, there are some announcements, and let's thank the presenters again. Thank you very much.
Thank you so much. That was a great set of presentations. I invite you to already get up. If you can keep your ears open and your mouth closed, please do get up and start moving around while I give you a few further announcements, because you've been sitting still for so long. Some of us are more the happy wiggle crowd. Others of you might be more the happy hop around crowd and jump. Either one is good to lift your energy again. So maybe we can get the slide for the special issue up in the background here. I have an announcement. If you don't know what to do with your summer, please do write an article for our special issue in the Journal of Industrial Ecology. That's going to be due September 1st. And it's about digital technologies and their environmental impact. So there's a lot of people here who have a lot of expertise in that area. We would love to see your contributions here. And no, you don't have to take a picture of this. We're going to send it around as well. I do want to announce it to all of you. Secondly, there is a number of lovely posters out there where you can leave a message. So go out there, grab a marker, leave a message for the future, find out what it's all about. Third and last one, if you're wondering why I changed my outfit, the fabulous artist from last night gifted me a pair of pants. I got to select them. So if you have not picked up any clothing items, look through if there is something that you like. If you already picked up something, or if you find something, I encourage and invite you to wear it tomorrow. With that, have a happy coffee break, and then we'll see you at the poster session upstairs. One more.
Just a quick announcement regarding coffee breaks. You all know that you can go downstairs to attend to the coffee break, but you can also go upstairs, where there is more space to talk to people, more food and more coffee.